4 cups of coffee deep. Yikes. Yeah. um, Good morning. So, I hope everybody's doing well, that you're staying safe and clean and clean hands and everything. So, um, today we're going to continue and finish up our discussion of work. And let's see. So, we're going to talk more about varying forces and also something called the work energy theorem, which allows us to connect this idea that we've been exploring work with the larger idea of energy. We'll see in the next chapter, we're going to talk about energy conservation. So this kind of is a nice segue into what we're going to be doing in the next chapter. So I know at the end of our last session, I talked a little bit about varying forces. I want to revisit that in a little more detail and also give you some kind of conceptual picture. So the main issue was that the main way in which this added complexity to our picture was that it requires us to use integration instead of just multiplying. But to put ourselves back in context, so far we've been man, my penmanship today is not very good. So far we've been using work equals F dot D, and we've talked about how that's also FD cosine theta, where theta is the angle between them. And we spent a lot of time sort of fleshing out what the dot product is. And talking about what that means, and we've looked at some problems with that, building up that our ability to use the dot product, to use that mathematical tool. And kind of the thing that we're adding to this is, and sort of conceptually, the picture, the simple picture that we had was, suppose you have, this was kind of our token simplified system. You have some block, and you pull the block some distance, displacement, and then we could find the work based on this. And the additional way that I want to talk about this is that you can think of this graphically too. So oops. So if we imagine this is f cosine theta, and we pull it through some distance x equals d, what that would look like is we're just multiplying these two things together. The f cosine theta is not changing as we pulled this object in this picture. So the work corresponds to the area of this. And in this situation, it's simple. The area is just a rectangle. Okay, so, but conceptually, why this is cool is because we're talking about this in the context of integration, and we often think of an integral as an area, or at least a definite integral anyway. And so conceptually, imagine now, come on, pen. Imagine now, in contrast to this, so I'm going to draw it just like, or I'm going to draw it so that the force is just in the same direction as the displacement, just to kind of simplify things. But what I want you to imagine is, as you pull this, suppose that the magnitude of the force changes. So maybe it starts out, it has some value, you pull it a ways, it increases, and then you pull it farther and it sort of drops off. So conceptually, what that would look like is, instead of it being just a rectangle, it got bigger and then it got smaller again. And the objective, though, is the same. Now we think of this force as a function of x. And what we want to do is still the same thing. We want to figure out what the area of this is. So the work becomes an integral of f of x dx. And let me see. So I've made a simplification here. So technically, this angle could be changing too. But we're going to limit ourselves to the situation where the displacement vector and the force are parallel for the time being. So conceptually, theta could be changing, the angle, both the angle and the magnitude of the force could be changing, but we're going to kind of do one thing at a time here. So to limit our discussion to force and the displacement being parallel. So it just makes it a lot easier to digest the problems. But I think you see what I mean, where, in general, the general case would be both the angle could be changing and the magnitude of the force could be changing. And in order to deal with this, we have to integrate. So I'm showing you this because I wanted to give you a little more context to the example that we talked about yesterday. So yesterday we talked about how, the kind of quintessential common system for a force that varies was a spring. And we talked about how the force for a spring is negative kx. Actually, it's usually a lowercase k here. Negative kx. And we talked about how, I think we talked about how this is the spring constant. It tells you how hard or how stretchy the spring is. And this negative sign tells you that the spring, is going to pull against you. And we looked at how if you integrate the spring force from 0 to some final length, so suppose, just to kind of recap where we were, if you stretch the spring from x equals 0 to, say, big X or X final, or whatever you want to call the end position, you get negative kx final squared over 2, and that this is the work that the spring is doing. And that work is negative because the spring pulls in the opposite direction as the displacement vector. And we also talked about, your pulling work would be then positive. So why I wanted to come back to this and flesh this out a little bit is because we can also think of this graphically. So the force in this situation is, it's negative, or it's kx. It's negative. I'm going to write it positive because, draw it as a positive thing because we care about the area, and it'll, the area of that will be the same for both the positive and the negative case. And if you're stretching it to, x equals some x final, what that would look like is, if you have a function, it's just a linear function, it would look like a line, like this. And the integral of that is the area underneath that. And we can show real simply that this is the same, it'll give us the same thing, because what is this? Well, it would be kx final. So the area of this thing would be k x final times x final times, we only want half of this, right? We only want the triangle, times a factor of 1/2. And so there you go. The work would be 1/2 kx final squared. And this is the same thing that we get from actually, analytically evaluating the integral. And let's see. So yeah, fx is the function f cosine theta. Sure. So we've limited ourselves to the case right now where, we're both our force and the displacement are along the x-axis. So the cosine theta has gone to 1, in other words, and we're considering just situations where it's simple because the angle is remaining constant and it's remaining 0. Rather than mix in both the dot product and integration at the same time, we're going to kind of do one or the other, just to make things a little bit easier on ourselves. Yeah, so that's conceptually, that's the idea. We're looking at when a force is varying, we have to be able to integrate it to find the work. So are there any questions? So that's a good question. What's the difference between work, the work done by the spring and the work done by the pulling force? So the issue with that is that, and we'll revisit this actually we can revisit this in the context of the work energy theorem that we'll talk about later in a few minutes here. But so the work spring, work S, this is the work that the spring is doing. Notice that the displacement, we're stretching it. The displacement is pointed this way, but the spring force is pointed this way. So when we integrate that, we'll get a negative work. And work P, so for pulling, or person, or whatever you want to call it. For this case, the displacement is positive, but the force pulling is also positive. So we're going to get a positive quantity. Yeah, so with regards to the jet launch problem, this is similar. I'll show you a couple example problems. involving area. So a way to think about these is you can also analyze problems where you're given a function, a graph, and you can find the area, and the area tells you the work. But to Guy's question, so that's the difference between the spring, the work that the spring is doing, and the work that the pulling force is doing. It basically has to do with the fact that the directions make one of them positive and one of them negative. And we can convince ourselves that these are the same size, because if we sum the forces in x, what do you have? You're going to have the pulling force minus the spring force at any position is going to be equal to 0. That's telling us that if you're just pulling it at a constant velocity, if it's not accelerating, then these have the same magnitude. So that's why it looks the same. We're kind of assuming, or it's baked into that, the fact that the magnitude of the pulling force and the spring force are going to be the same. Okay, so yeah, to Evan's question about the homework problems, let me show you a couple example questions that will hopefully kind of connect with that. So let's see. So there's different ways to think about this. Uh-oh. Gah. So for example, here's a question. I think so. Most folks had some. So we'll look at one analytical question, and then we'll look at a graphing question. So this would be the analytical version. Now, instead of a spring that has kx, we have a more complicated spring, quote unquote. So some kind of exotic spring that has a weird force behavior. And so let me just read you the question. Work with varying force. The force needed to hold a particular spring compressed an amount x from its normal length is given by F equals kx plus ax cubed plus bx to the fourth. So how much work must be done to compress it by an amount capital X starting from x equals 0? So yeah, so the area under the curve is going to be the work. We'll talk about a question that's similar to that in a second. So this may look a little strange, but you can think of this force law, F equals negative kx. That is sort of the idealization. That's the spring when you're keeping it in its close to its equilibrium length. If you were to take the spring and like really crank on it and stretch it out, you can, if you kind of exceed the spring has a finite length, right? So if you pull it too far, it can have behave differently. And so these additional terms like x cubed, x to the fourth, those are not necessarily like just made up. Like it may be a more realistic representation of how a real spring would behave. But if we want to find the work, what do? We're going to need to integrate the force. Let's draw a picture. I'm kind of getting ahead of ourselves here. So it's the same kind of situation. The spring has some equilibrium length. We're going to count that is basically where x equals 0. And you stretch it to some x equals big X. I'm not super fond of this, of denoting a variable, one of your limits of integration as something that looks really similar to the variable of integration, but I suspect that you've seen stuff like this. So I could also call this, why don't we call it like x final? So in other words, the displacement is from 0 to x final. And again, this is a situation where the force, oh, wait, I screwed up here. This situation, it brings up another thing. So I wasn't modeling very good here. I was thinking of our stretching example, but notice this is a compression example. So the math is exactly the same. So I can't draw a compression versus stretching situation. They all so instead of stretching the spring, we're going to compress it. And like I said, the math is exactly the same. The spring that you might think of is different though. So instead of like a slinky or something, imagine where you stretch it. Imagine like a coilover spring in a car or something, or maybe like a mattress spring. So instead of stretching it, you compress those springs. So if we compress this spring from x, its equilibrium position to big X, or we could call this X final, we can find the work by integrating this spring force over those limits. So in other words, we're going to go from 0 to X final. So what does that look like? Put in our force law. Thankfully, it doesn't make things that much more complicated. This is going to follow the same rule that we use for powers, integrating x to some n. So we integrate this. You would have kx squared over 2 plus ax to the fourth over 4 plus bx to the fifth over 5. And then we would be evaluating this from 0 to x final. So that would be kx final squared over 2 plus ax final to the fourth over 4 plus bx final to the fifth over 5 minus, 0 squared over 2. So all these would be 0. So the work that we're doing in this to compress this spring would be just this, the kx to the squared over 2, ak to the fourth over 4, or ax final to the fourth over 4, bx final to the fifth over 5. So it's the same, it's a problem that's set up very similarly, but a little bit more complicated, a little bit of a twist on it because we're talking about in compression rather than stretching of the spring. But that hopefully that is not too foreign or not too much of a leap compared to our default, compared to the simple kx. Let's see. So x final would be negative, or would x final be negative? Let's see. So I was being kind of sloppy here. The force that we're exerting on the spring, we're pushing it. So remember when we were talking about a spring and extension, the spring is always going to resist what you're doing. So we're looking for the work done to compress the spring. So the force and the displacement are actually in the same direction. So we're treating it as if it's positive. So let me put down here. The work that we're doing to compress it is going to be positive because because the force that we're exerting on it and the displacement are in the same direction. But that's an excellent question, Samuel, because you could imagine I could draw this, the exact like mirror image of this, and it shouldn't affect the sign, in which case the sign of the work, that is, in which case, our coordinates would have changed, but that's not going to impact the sign of the work because because the force, now the force is pointing this way, but the displacement is also pointing this way. So does that clarify that? That's an excellent question, I have to say. Cool. Okay, so like I said, this is an example of sort of the analytical approach, and there is one homework problem. There's one homework problem. Yeah, so to your question, Luke, there's one homework problem that involves integration like this. So like the rock embeds in the mud or something like that. So that would be relevant for this. You're going to have to do an integration problem. So that was sort of an analytical type problem. And then this is sort of a graphical problem. So like I presented to you, another way to think about this is to imagine the area underneath the curve for the force curve. So here is an example like that. So this is relevant to that homework problem of the aircraft carrier. So for this one, the force on a particle acting along the x-axis varies as shown. Determine the work done by this force to move the particle along the x-axis from x equals 0 to x equals 10, and from x equals 0 to x equals 15. So, 1 second here. The mud. Yeah. So remind me about the mud problem. We can talk about that at the end. So these graphical type problems, it's the same thing. We need to integrate, right? Except now instead of f as f as written out as a function, we have a graph that shows us what how the function behaves. So what we need to do is the work is going to be the integral from 0 to 10, at least for part A here. Our f of x. And again, this situation, it's simplified somewhat in that, notice the force is acting along the x-axis, and our displacement is along the x-axis, so they're parallel. or our displacement is the x-axis. So when we go to integrate this, what we need to do is find the area of this thing. And so it's kind of nice, I can write directly on this here. From 0 to 10, we need to find the area of this first trapezoid-looking shape. So you can imagine, you would break this up probably into like some triangles and stuff. And looking at that, this looks like about 3 times 400 times a factor of 1/2, because we only want, this triangle, plus this is, 4 times 400 plus, another triangle of the same size. So when you add up those pieces, you'd get something it's basically, 7 times 400. So 2,800 joules would be the work done on the particle between 0 and 10. And then for the second part of this, we have to add to that the work here. But notice this work is going to be negative. So let's find the area for that part. So from 10 to 15, it's kind of the same situation. It's a little smaller and maybe harder to break out, but it would be something like, a couple triangles. So this looks like about, let's see here, approximately 3, maybe 1.5 times negative 200 times a factor of 1/2, plus, 2 times the negative 200 plus another triangle. So when you add those pieces up, you get about negative 700. So the work from 0 to 10, or sorry, 0 to 15 is going to be that 2,800 minus 700, and so it would be about 2,100 joules. Yeah, I think if you knew the dimensions, if you have like a formula, yep, you could use that. Let's see. So I'm not sure your question, Anthony. 3,000? So if you're talking about a homework problem, one thing that you may notice is you'll have different numbers potentially. So, but with this problem, I mean, we're kind of doing our best interpreting the diagram. So let's see, Luke, to your question, what we've done here is we've done a graphical integral. We found the area. Although we've noticed that the area from 0 to 10, so for the first part, we've just found what the area of this is. And then for the second part, we found the area of this smaller bit. But this piece is negative. You can think of that as, something has changed direction. For example, if you had the force pointing in the same direction, so maybe like if you had a particle that was moving on a surface and the friction was pointed one direction and then you change direction, the friction is going to point the other direction. Wait, no, that wouldn't work. They'd be in the same direction. it would be a situation where a sign or something changes so that you get a negative piece. So that negative contribution is going to subtract from the overall, from the positive piece, and you would end up with the total work being less when you go from 0 to all the way to 15. Okay. I think I probably just made things more confusing, Luke. Are there further questions on this, like graphical approach? Oh, where the numbers are coming from. Well, here, let me so basically I'm just looking at this triangle. So the base of this is about 1.5. The height of this is about negative 200. And then we pick up a factor of, 1/2 because it's just this triangle. Yeah, no, it's not. I mean, it's not like a great picture. The graph is kind of small. It's more just to get across this is how you would go about it. So I think it's relevant for one of the homework problems as you do a graphical problem. So I want to make sure we have enough time to talk about our last topic. So the last thing that we need to make sure that we discuss, because it's relevant for your homework, is the section 7.4. It's this work energy theorem. And this is kind of cool because it starts to connect what we have been doing, forces, and now more recently work, to the larger idea of energy. So, and there are different kinds of energy. I suspect if you've had a little bit of physics before, you've talked about potential energy, kinetic energy. So the kind of energy that we're concerned with for this is kinetic energy, because we're going to talk about a relationship between work and kinetic energy. So kinetic energy is, I think of it as just the energy that's associated with an object's velocity. So, or associated with motion, things that are moving have kinetic energy. And it's written in your book as K. I think I like KE because it's obvious this is kinetic energy. And the formula for kinetic energy is 1/2 mv squared. So in other words, if you know an object's velocity, the size of its velocity, you know its kinetic energy, provided you have the mass. So we introduced this here, but we're going to make a lot of use of this in the next chapter when we talk about energy conservation. So the relationship between work and kinetic energy is the following. The net work on an object is equal to its change in kinetic energy. Okay? So in other words, the total work is going to equal 1/2 mv final squared minus 1/2 mv initial squared, the change in kinetic energy. So this is relevant. Remember our spring problem, right? Where we're talking about the work done by the spring and the work done pushing the spring or pulling the spring or whatever specific situation we were talking about. So let's talk about let's just think of the stretch case. The spring is pulling this way, and we were pulling it this way, and we found that if we stretched it some distance x final, that the spring was doing negative kx 1/2 kx final squared, and we were doing 1/2 kx final squared. Well, if you look at the network, if you add these together, it's 0. They're the same size, but one's positive and one's negative. So as a result, this is kind of not not the most interesting case, but this would mean that the change in kinetic energy is 0. So if we just stretch this thing, the spring is doing work, we're doing work, but the total work, the net work, is 0. And so there's no change in the kinetic energy. So this is similar to examples I showed you, like consider this trivial example with the coffee cup, right? Where we lift the coffee cup. So if you lift the coffee cup, the work that you're doing on the coffee cup mgh, and the work that, let me put it this way, work that gravity is doing on the coffee cup, they sum to 0, because remember, one was positive, mgh, the other was negative, because the force of gravity is pointing down, mgh. So you sum them, and so the change in kinetic energy in this case is going to be 0. So this is in contrast to the situation. Think about, instead, what if you take your coffee cup and instead you drop it? Okay. So you're no longer going to be doing work on it. So let's drop it through some distance d. The work of gravity in this situation is going to be positive because it's pointed in the same direction. It's going to be the force times the distance. So this is or let's call it height. How about? Now notice in this case, this is the only work that's being done. So the net work is going to equal the change in kinetic energy. So mgh is going to equal 1/2, mv final squared minus 1/2 mv initial squared. So this initial, v initial, is going to be 0 if we're dropping it. Notice we have mgh equals 1/2 mv final squared. We can cancel the m that appears in both. And then we could solve this for the final velocity of the coffee cup. We'd get, we get the square root of 2gh. So we've used the work energy theorem to find a velocity. Okay. But something that's kind of cool about this is that we have done this problem before, right? So remember, we looked at this. You throw an object out a window or something like that. You can get the same thing. Consider from, think back to chapter 2. if we're thinking about kinematics in one dimension, we had this expression, v final squared is v initial squared plus 2ad. Well, if you're dropping it, this would be 0. Our acceleration would be g. V final square root of 2gg. Or, our d is height as we have it written. But this is the same thing. So this is, I think this is an example of how, as you progress, as you learn more physics, you're going to have more problems that you're able to solve, but you're also going to have more ways to solve problems. Which I think is kind of cool. So now this is kind of the, like a really simple example. There's some, let me show you like another example just so you have another thing to kind of think about. So we use this one to find we use the work energy theorem to find velocity, but we could also do things like find the force. So let me show you another example. So let's see here. I think it's this one. No. This one? No. Shoot, I can't find my... 1 second. It's too small, I can't read it. Sorry, having trouble with my clipboard. Oh, nah. Are you kidding me? So usually I can find these pretty easily, but... No. What is going on here? Okay, one more shot. Huh. I can't seem to find the example problem. Sorry, 1 second. I'll just I can tell you what it is. So the problem is, consider a baseball has a mass of 145 grams. It's traveling at 32 meters per second. It moves a fielder's glove backward 25 centimeters when caught. And what we're interested in is what is the average force exerted by the ball on the glove? Okay. Yeah, so the mud question. Let's see. Yeah, we can talk about that real quick right now. So this, the question about keeping, you have to find the work that's done by gravity in addition to the work that's done by the mud. So you have like an object, it hits the mud, it embeds in the mud. Hello. So it hits the mud and then it like embeds in here. and you found the work done by the mud, you're going to get by integrating the force, and there's an expression that depends on y, I think. And then you also need to get the work done by gravity, and that's going to be positive, if I recall, if I'm thinking of this, if I'm remembering this right, because your displacement is positive and the force of gravity is also positive. So, oh, no worries. I think that was the. Does that help with the mud question? You have to find the work done by gravity as well. So we'll kind of bracket that off to the side for a second. But yeah, I don't want to run over time too much here. So this baseball question, we want to know the force. So basically, why I'm showing you this is because this is an example where we're solving for force instead of solving for. Oh, MGH doesn't work. Huh. Well, I'll tell you what. I'll investigate this situation and then I can post something in Teams. So don't worry about this. We'll whoa, hello. We'll table this for a second and I can address that in Teams. So, with regards to this the baseball question, you know, the baseball's moving, you catch it in a glove. Oh man. And then that combination moves back some distance. And we want to know the force exerted by the ball on the glove. So there's really the force, it's a pair of forces. So the glove is going to push on the ball, and the ball is going to push back on the glove. Now, the network is not zero because there's only one force that's acting on the ball, and that's what we'll use to find the force, because we know that the network, now we're talking about the ball, is going to be equal to the change in kinetic energy. So the network is going to be the force that we're after times that displacement, and we're given the displacement. That's going to equal 1/2 mv final squared minus 1/2 mv initial squared. Now in this case, the final velocity is 0, so this piece would be 0. And so we have a relationship between the force, the distance, and the initial kinetic energy. We can solve this for the force. And let's see here. When we do that, when we evaluate this, so we know the velocity, we know, so this would be 1/2 oops. So the mass was 0.145, it's 145 grams times 32 squared divided by a distance of 0.25. When we evaluate that, we get 300 joules. Okay. So I should say there's a sign issue here. This, wait a second here. Yeah, so when we're talking about the ball. So initially we're talking about the ball. Notice that the force is in the opposite direction as the displacement. So this would be negative. So this whole thing would be positive. Now, if we talk about the force or the work that's done, or the blah, blah. Wait a second. No. This is not joules. This is newtons. Sorry. Sorry, I got turned around there for a second. So the size of the force exerted on the ball would be 300 newtons, and the ball would exert an equal-sized force on the glove. So this is the size of that force, 300 newtons. Sorry, that was sort of a confusing explanation there. So the main takeaway with this is just that we've used the work-energy theorem instead of to calculate a velocity like we did before. You know, if you drop an object or something like that, you can also do things like find forces. And we're kind of running up against our time limit. There was one other question that I wanted to show you. So if you have class, I don't want you to I don't want to step on your next class, but so you can, feel free to do what you got to do. But I'll just post this question at the end of the video here, and that way, if you want to, you can look at it later. And it's relevant, I think, to the homework, but it's kind of an interesting question. So, and this one I do have loaded in my thing, I think. So you can also do things like find the distance. So, there it is. Oh my God. Kidding me? Technical problems today. My apologies. So here's a question for you. So this is kind of a cool application of this work-energy theorem, is to think about situations like if you want to know stopping distance. So you can relate the force of friction to the work done by friction to the change in kinetic energy. And I think there's a problem in your homework that's likely like this. So here's the situation. So if the speed of a car is increased by 50%, by what factor will its braking distance be increased? Assuming everything else is the same. So the situation, we have a car. It's zipping along at some velocity, and you put on the brakes. It's going to skid, say. That's not a very... And come to a stop over some distance. And the question is, we can relate the work through the work-energy theorem to the change in kinetic energy. So the work in this case is going to be the force of friction. So sorry, I should say there's going to be a force of friction. Our displacement is pointed this way, and our force of friction is pointed back. It's always going to be in the opposite direction. So we would have a force of friction times distance. That'll be negative. The work will be negative because those things are pointed in opposite directions. It's going to equal the change in kinetic energy. So the final velocity, 1/2 mv final squared minus 1/2 v initial squared. And the v initial would be our v naught, that the initial speed of the car, but if it's slowing down to a stop, this would be 0. So in other words, we have a relationship between the force of friction times the distance is going to equal 1/2 mv squared. And so we can solve this for the distance. I'll put in v naught squared for how we have it in the picture. Now, if everything else is the same, the force of friction is going to be the same. The mass, of course, is going to be the same. The only thing that's changing is the initial velocity. So if the initial velocity increases by 50%, that's the same thing as saying v naught is going to increase by plus 0.5 v naught, i.e. this is 1.5 v naught. So in other words, our distance, our new distance is going to be 1/2 m 1.5 v naught squared over the force of friction. We can pull out that factor of 1.5 squared. And so this d prime would be 1.5 squared times what we had before, and we could call this, why don't we call this d naught? So in other words, this will mean that our d prime is going to be 1.5 squared times our original distance. This is something like, when you multiply that out, you get 2.25. So this is kind of interesting. Increasing the velocity by 50%, the stopping distance increased by more than 2 times. So in any case, I wanted you to have this problem as a reference. Maybe it'll be useful for you. It's another context where we're talking about using the work energy theorem. In this case, we're talking about friction to solve for a distance. So you can solve for distance, you can solve for force, you can solve for velocity. You can see that this opens up some, sort of a menu of different kinds of situations that you can analyze. In any case, sorry for going over time. I really don't mean to step on your step into your other classes, or I'm not sure if people have classes at noon exactly, but I still don't want to abuse your time. So that's everything. This should have more than enough stuff for you to help you solve the homework problems. I will look into the mud problem and get back to everybody. So I can post on Teams about it. Does anybody have any questions? Sorry, I had technical difficulties there today. I could not seem to get my post the question thing to work very well, which kind of got me a little messed up. Questions? Let's see. Yeah, the homework's due tonight. I'll track down what's up with this one question, and I can post some guidance. So, kind of broadly speaking, it's kind of cool, I'll tell you, to transition from talking about forces. So, and I think you've noticed, it's tricky. You got to keep track of angles. You have to keep track of directions of everything when you're working with forces. We had to learn about this mathematical tool, the dot product, to deal with keeping track of directions. Where we're headed, talking about energy conservation, that'll be, it's not a vector. So it's a lot easier mathematically a lot of times to deal with because you don't have to pay so much attention to the directions of everything. Working with scalars is often easier, so I think you'll find that to be kind of nice moving forward. So that's kind of where we're headed, is to work more with energy. So other questions? Well, I sure, I appreciate your patience with the online stuff. It's kind of a little bit of a rodeo, so um, feel free to, reach out to me with feedback, or if you've seen something like in in another course and you're like, man, this works really well. Let me know. We want to do what works the best. So otherwise, if folks don't have any questions, if I'll see some of you tomorrow in lab, and if I don't see you tomorrow, have an excellent weekend, and otherwise we'll see you tomorrow. So